goes to the ground state. Right?
No, we don't fully fill the excited states. What we say is in a Bose-Einstein condensate, there will be a number of particles in the excited states. We calculate them. We subtract it from the full number of particles, and that gives us the number of particles in the ground state, which is the Bose-Einstein condensate.
We fully fill them in the sense that there's a criteria to work out, right? There's a maximum number of particles that can go in excited states.
No.
In BEC.
All the particles can go to the excited state.
No, the
Critical temperature.
You say the critical temperature is, you set mu is equal to 0. That is the definition of the Bose-Einstein condensation. So you are right at the critical point. What does that mean is the chemical potential is already 0, so Z is 1. But there are yet not many particles in the ground state. So all the particles are still in the excited state, but chemical potential is already 0. That is the definition of the critical temperature. If your temperature goes below that, the number of particles in the excited states cannot be equal to the total number of particles. It becomes a smaller number. The remaining is in the ground state.
So at the critical temperature, there's no upper limit on how many particles can be in excited states? It's whatever particles are already there.
You say at the critical temperature, you say this is the number of particles in the ground state. Well, let me write it this way. This is the total number of particles. And N0 is Z over 1 minus Z.
It's not mu, right?
Hmm?
It's not mu.
No, it's not mu, it's epsilon. Now, the definition of Bose-Einstein condensate is mu is equal to 1, 0. Let me say 0 plus. So, N is given by this number.
What do you mean by 0
Hmm?
plus the price?
You see, look at this expression. If Z is equal to 1 and 0 is infinite. We don't have infinitely many particles anyway. We have a finite number of particles. Mu is close to 0. No, sorry, it's 0 minus. It has to be negative. Mu is close to 0, but not exactly 0. It is very close to 0. But if mu is very close to 0, at least within this integral, I can set Z equal to 1. And so this should be satisfied. So which tells me that N0 is still 0. 0 meaning negligible compared to N. I still have, of course, a number of particles in the ground state, but the number of particles in the ground state is negligible compared to N. That is what I mean by N0 is equal to 0. But then if you look at this integral, for beta larger than beta critical or T less than T critical, you see, if you increase beta, the integrand becomes smaller at any value of epsilon. So the integral itself becomes smaller. It can no longer be equal to N, it is less than N. Since it is less than N, the remaining particles, you see, look at this definition. If the first term is less than N, then N0 should be larger than 0. But is there a maximum number of particles in the excited state? No, the number of particles in the excited state is given by this integral over here. There's no upper limit. But what happens right at the critical point, at the transition point, is we have this one. If this condition is satisfied only at the critical temperature. Above that, well, mu is non-zero, And we should adjust, we should choose mu such that this number is equal to n above the critical temperature. Below the critical temperature, well, this is what n is, because chemical potential cannot be larger than 0. This is the number of particles in the excited state. The rest are in the ground state. Why we say that this is the number of excited particles? You see, G epsilon is proportional to square root of epsilon. So that integral doesn't take into account the number of particles in the ground state. Above the critical temperatures, they are negligible compared to all the number of particles we have, but below the critical temperature, they are not negligible. So let's go back to our fermions. You see, these are the equations we have. This is U. This is the equation that will tell us what F is, what Z is. And this is PV related to U. And yeah. And let me also write PV is KT F5/2 of Z F3/2 of Z. Now let's look at various limits. The first one will be when Z is around 0. You see, Z was e to power beta mu, and mu can be equal to the Fermi energy. It can be a positive number, it can be a negative number, it can go to minus infinity. There is no limit on mu. So Z close to 0 means beta mu goes to minus infinity somehow, in certain limits. We don't know what that limit is yet, but we will discover that. So let's look at this one. This is the equation that will tell us what Z is. But in order to do that, I need to know what F3/2Z is as a function of Z. Well, we had already studied what G is for the both G nu. So this F nu is 1 over gamma nu 0 to infinity dx x to the power nu minus 1 e to the power x plus 1. And G of nu minus 1. Well, there's an interesting relation between F and G. And if you remember, we already know what G nu of Z is equal to sum over n Z to the n divided by n to the power nu. Yes. Was it n to the power nu or n to the power nu plus 1? I think it was n to the power nu. If you remember the derivation, basically, we said 0 to infinity dx x to the power nu minus 1 divided by e to the power x z to the power minus 1 minus 1. This is equal to 0 to infinity dx x to the power nu minus 1 z times e to the power minus x divided by 1 minus z times e to the power minus x. Now we Taylor expanded it as a function of z. to the n. Here n goes from 0 to infinity. So this is equal to n from 0 to infinity, z to the power n plus 1. 0 to infinity integral dx x to the power nu minus 1 e to the power minus n plus 1x, which is n from 0 to infinity z to the n plus 1 divided by n plus 1 to the power nu of gamma nu. Yes, this is g of nu. Now, let's try to relate f of nu to g of nu. In fact, there is an interesting relationship between the two. First of all, if I want to relate these, somehow I have to convert that plus 1 to minus 1. Well, let's just multiply this by minus 1, which will give me minus 1. Well, the reason why I wrote it plus 1 minus 1 is so which will be 1 over gamma nu well, if I take those two terms, they cancel in the numerator and denominator, and I end up having 1 over z to the minus 1, e to the power x minus 1. And then I have minus 2 this is f nu of z, which is g nu of z, this term, minus 2 Now, if you look at this one, let me make a change of variable. Let me call 2x, y is equal to 2x, or x is equal to 2y over 2. So f nu of z will be g nu of z minus 2 over 2 to the power nu. This 2 is this one. I have from dx and x to the power nu minus 1, I get a divided by 2 to the nu. dy from 0 to infinity, y to the nu minus 1, divided by z to the minus 2, e to the power y minus 1. So f nu of z is equal to g nu of z minus 1 over 2 to the power nu minus 1 g nu of z squared. Now later on, when, for example, when we look at what happens when z is close to 1, f nu of 0 will be g nu of 1 minus 1 over 2 to the nu minus 1 g nu of 1, which will be 1 minus 1 over 2 to the nu minus 1 zeta of nu. Because g nu of 1 is just a zeta, Riemann zeta function. Okay, that is what we will use later on. Let's look at this one. We already know the expansions. F nu of z. Let me just keep the first correction, the z squared correction, and remember, g nu of z is z plus z squared over 2 to the nu higher order terms. So f nu of z is from g nu of z, I have z plus z squared divided by 2 to the nu plus terms of the order of z squared minus 1 over 2 to the power nu minus 1 of z squared plus of the order of z to the 4. So this term is from this one over here. So what we have is z plus z squared over 2 nu 1 minus 2 z plus of the order of z cubed this is f nu of z. Now remember, n lambda cubed over g is f3 over 2 of z, which is z minus z squared over 2 to the power 3 over 2. This will tell me what z is up to the first correction in n lambda cubed over g. You see, we said that z is much less than, no, z is close to 0, approximately 0. Now this result tells me that this means n lambda cubed over g is close to 0, which tells me that it's a rarefied gas at high temperature. Rarefied gas means n is small, and high temperature means lambda is small. So this is why, although we started by saying, okay, let's look at what happens when z is 0. Z can be 0. So let's see what happens when z is 0. This tells me that z is equal to 0 basically corresponds to high temperature limit. So let's find what z is. Basically, I will repeat the derivation we did in the Bose-Einstein condensate case. So z, let me just call this number. Let's give it a name. N lambda cubed over g, let's give it a name. Let me call that kappa. I just don't want to write n lambda cubed over g and over and over again. So z should be kappa plus delta kappa squared plus terms of the order of kappa cubed. I can consider a Taylor expansion of z. Now, if I put this expression into this equation over here, kappa should be equal to kappa plus delta kappa squared minus 1 over 2 to the 3 halves kappa squared plus terms of the order of kappa cubed, which tells me that delta is equal to 1 over 2 to the power 3 halves. So these two cancel. So I have to have delta is equal to 1 over 2 to the power 3 halves. So z is n lambda cubed over g plus 1 over 2 to the power 3 halves n lambda cubed over g squared plus higher order terms. This is my z. Let's look for the pressure. Well, or let's look for the energy. PV was basically proportional to energy. This is my energy. This is what we had derived before. So this is equal to 3 over 2 kT. Remember, we are looking at the case z is close to 0. So I can just Taylor expand both the numerator and denominator. Denominator gives me z. Well, this is the expansion of f nu to terms up to second order in z. Z minus z squared divided by 2 to the power 5 over 2 divided by z minus z squared divided by 2 to the power 3 over 2. Well, I can cancel one factor of z both from the numerator and denominator, plus terms of the order of z squared, let's say. This is 3 over 2 kT, 1 minus z over 2 to the power 5 over 2 times 1 plus z divided by 2 to the power 3 over 2 plus terms of the order of z squared. Well, I will just multiply them out. 1 plus z over 2 to the power 3 over 2 minus z over 2 to the power 5 over 2 plus terms of the order of z squared. Which is 3 over 2 kT, 1 plus z over 2 to the power 5 over 2 plus terms of the order of z squared. This is u over n. Remember, the 1 is the classical limit. The z over 2 to the power 5 over 2 is the first correction. Well, we also calculated what z is. This is our z. So let me just put it over there. You see the first correction in n lambda cubed over g is the first term. U over n is equal to 3 over 2 kT, 1 plus 1 over 2 to the power 5 over 2, n lambda cubed over g plus higher order terms. This is the energy. And remember, pressure, we had already derived the relation between pressure and the internal energy. PV is equal to KT, NKT, 1 plus 1 over 2 to the power 5 over 2, n lambda cubed over g plus higher order terms. Now, if you remember, when we were looking at the boson gas, we also calculated that first correction, and the first correction was minus. And we said that, okay, that is expected because bosons effectively, even if they are not interacting, effectively due to their statistics, they're an attractive potential between bosons. But for fermions, the potential is repulsive. That statistical potential, let's say, is in a sense what causes the fermions not to occupy the same state. They will be pushing each other apart. But if they are pushing each other apart, what will happen is, if you just imagine this gas within a box, as the particles are moving towards the walls, well, they will be pushed away. So they will hit the walls faster, exerting a larger pressure. So we already expected the pressure of a fermion gas to be slightly larger than the pressure of the Maxwell-Boltzmann gas, or which we expect to be larger than the pressure of a boson gas. And that is in fact what we are seeing in these signs. This was a minus sign for a boson, and but it doesn't exist for a Maxwell-Boltzmann gas.
Could you repeat the argument again, sir?
You see, you remember we had looked at two particle density of states for identical particles.
Okay.
And then we derived an effective potential between fermions and bosons. You see, we started by looking at the non-interacting particles, but when we took into account their statistics, we had derived a result which basically looks like we could have obtained the same result if we had treated the particles as if they are Maxwell-Boltzmann particles. That's same but distinguishable, with an additional potential. And that additional potential was repulsive for fermions, attractive for bosons. So, I mean, we are always looking at the ideal gas, no interactions. But if you have, let's say, attraction between the particles, you see the pressure on the walls is created by the particles hitting the wall. So if as a particle is moving towards the wall, if there's an attractive potential between the particles, it will slow down. So it will transfer less momentum and exert a smaller force. That was the case for bosons. In the case of fermions over here, there's an effective repulsive potential between them. So as a single fermion is moving towards the wall, all other fermions are pushing it away. If they are pushing it away, they will get faster and hence exert a larger pressure, a larger force on the walls. So we expected the fermion gas to be larger than the boson gas. So that is the reason why we have this sign difference between fermions and bosons. PV is larger than NKT for fermions and smaller than NKT for bosons. Any questions?
Do the terms in higher orders alternate? So for bosons, the first correction term is negative, and for fermions it's positive. But for example, not the second but the third correction term, is the sign again flipped, or
I don't really know. And I don't really care that much, to be honest. Well, but what will happen is this function f of nu of z. This is essentially from n is equal to 0 to infinity minus 1 to the n, z to the n plus 1 divided by n plus 1 to the power nu. This should be the expansion. You see here the various coefficients alternate for fermions. For bosons, all the coefficients were positive for the G nu function. I can't really see easily how that alternating sign will affect this ratio. So I can't really say what will be the effect on U. Now so any questions about this? Well, of course, now we have the energy, we have the pressure. If you want to specificate, just take the derivative of the energy with respect to temperature. Now, in the last few minutes, let's just look at what happens when we have T is equal to 0. This is called a degenerate Fermi gas. This is somewhat an easy limit to consider. Well, I will need the density of states. You see, we had seen that in this limit, the Fermi-Dirac distribution as a function of energy just becomes the step function. Now, what is the Fermi energy? Well, let's look at what this should give me the total number of particles. Now the Fermi-Dirac distribution is just a step function which basically tells me that this limit doesn't go up to infinity, but it goes up to Fermi energy. What is the density of states? Well, G times 2 pi V over H cubed, 2m to the power 3 over 2, square root of epsilon, this is n, or small n should be equal to 2 pi over H cubed, 2m to the power 3 over 2, G is the degeneracy factor, epsilon Fermi to the 3 over 2 times 2/3. Well, this is the definition of the Fermi energy. The density should be equal to 4 pi over 3 H cubed G divided by 2m to the power 3 over 2 epsilon Fermi to the power 3/2. What is the total energy? Well, that's again, the total energy of the system will be the integral from 0 to infinity of the density of states, the Fermi-Dirac distribution, times the energy. Well, the Fermi-Dirac distribution is again the step function, so this is 0 to the Fermi energy of the epsilon. Now G epsilon is again this number. There's the degeneracy times epsilon, so this is G times 2 pi V over H cubed, 2m to the power 3 over 2. The remaining integral is the Fermi energy raised to the power 5 over 2 times 2 over 5. Well, let's see. G times 2 pi V over H cubed, 2m to the power 3 over 2 epsilon Fermi to the power 3 over 2 times 2/3 times epsilon Fermi times 3 over 5. Now, the reason why I wrote it in this way is this integral over here is nothing but the total number of particles. So U is equal to 3 over 5 n times epsilon Fermi. Or U over n. The average energy per particle is 3 over 5 times epsilon Fermi, which is, by the way, is... So we also know the pressure, by the way. Pressure, PV, remember PV was 3 over 2U. This is for any temperature. Well, this is 3 over 2 times 3 over 5 n times epsilon Fermi. So PV, if I didn't get any factors wrong in the board, PV is equal to 9 over 10 n times epsilon Fermi, or pressure is given by, this is the pressure. You see, even at 0 temperature, we have a large pressure.
This pressure is due to the Fermi particles fermions.
Yes.
Indeed, close to Fermi energy. I mean, the gap.
Well, you see,
The other ones are frozen.
not really. I mean, they are not frozen in the sense that it's not that they are not moving. In fact, some of them have a very large energy. They are frozen in the sense that they cannot be excited anymore. Because if you excite them, the state they would go is already occupied, so they cannot go there. So all the particles, in fact, will contribute to this energy. Now we said, okay, one last thing before we go. You say this is the definition of Fermi energy. This is a definition. So you can define the Fermi energy whatever the temperature is. And at T equal to 0, the chemical potential will be equal to the Fermi energy. At non-zero temperature, it will not be equal to the Fermi energy. But, I mean, the Fermi energy is a property of the material, given by this number. So what is n lambda cube? Lambda cube is h cubed divided by 2 pi m kt to the power 3/2. This is at an arbitrary temperature. This should be equal to 4 pi over 3 h cubed. Well, there's a over g over here. Four pi over 3 h cubed. G's are cancelled. 1 over 2 pi to the 3 over 2. Sorry. Yeah, no. Let me look at my so this 2m to the power 3 over 2 is in the numerator, not in the denominator. So these two m's cancel. H bar cubes also cancel. So this 2 pi cube is in the correct place. No, it's just 2 pi. So let me define epsilon Fermi as k times T Fermi. So n lambda cubed over G is, this is still n, so there's no n over here. This is T Fermi over T to the power 3 over 2 multiplied by some number of the order of 1. I have pi's, etc. Well, in the case of fermions, we have a single energy scale. That is T Fermi. And lambda cube is equal to 1, this basically tells me that T is around T Fermi because of this relation over here. So we don't really have two different energy scales, one energy scale actually. Although when we wrote n lambda cube, remember before I said that this defines an energy scale. We have a Fermi energy scale defined in a different way, but they are basically the same. So it's not a problem with two different energy scales, but a single energy scale. So high temperature and low temperature, we can effectively decide on it by looking at the Fermi temperature, which corresponds to 10 to the power 4, 10 to the power 5 Kelvin. typically. Any last questions?
Are we going to continue with this one?
Yes.
Because it's the, for me, it's the more interesting one.
Hmm?
For me, it's the more interesting one. Low temperature case is the more interesting one.
You see, this is what happens at t equal to 0, strictly at t equal to 0. But what happens if temperature is small but not equal to 0? For example, if you would like to calculate a specific heat, we should know how the energy changes as a function of temperature at low temperatures. That is what I left for Wednesday. That is where we will pick up. So see you on Wednesday in the lecture. Yes.
On Friday, the